Good morning. Now it's fourth lecture on QBI, and before I start, do you have any questions from last week? Then let's go. Today I'm going to talk about segmentation and discrete structures, and let's see, that should work. Hello. So now it works. So I'm going to talk a little bit about first a little bit qualitative approaches, a little bit review from what we did last week, and then take a detour into the image formation process and what we can see there and what interpretations we can do and not do. Then switching on to thresholding and how to implement it. I'm going to round off with the morphological image processing and finally partial volume effects. So as usual, we have a bunch of modules that we need to load, just to make sure that they are loaded. There they are. And first of all, we have our applications where we do some image. Here is an image of the brain cortex in brain imaging. And the question is where it is, first of all, and do we have sufficient contrast to see it? And it's easy to make a decision if you have just two distinct materials. You have something and you have void, or you have some embedding medium. That's a quite easy task to segment. But it could be that we have more variation in the data. We could have multiple phases, like in the body we have different tissues, we have bones, fluids, and so on. And all that gives a more complex image that you need to analyze. And there could also be holes in the data due to artifacts that we may want to detect or not detect. We could also do fossil segmentation. And then we have this brain cortex task, which is not very trivial because it's about finding this region here. And compared to the other parts, it's not so obvious what it actually is. There will be, I think next week, some attempts on doing it, but you will see it's a tricky thing. Then there is some literature. John Ross always gives us a nice introduction. And then there is this article on Wikipedia about the ROC curve. I'm going to say more about that one later, anyway. So, and then there are also some metrics to work with that we touched a little bit upon already, but we'll see more about it now. So we have different reasons to make our experiments. One is just to explore some object. In our group we do a lot of cultural heritage investigations where we have bronze statues and we want to see what is inside, how they were made. And then it's only more about visually exploring, seeing what's inside, and not so often maybe that we want to quantify anything. However, what we are mainly about here in this class is testing a hypothesis that we want to measure something and say it is that or it's not that. And it could be that we want to see if the temperature has an effect on the bubble size in some process. It could also be that the cell shape varies with different conditions, or canal volumes if they make the bones weaker, and so on. And depending on what you want to question about, you have to apply different methods to measure this. So if we do exploring, we can have some image. This is kind of a sketch of a standard cell. What it looks like in the reality is maybe something like this. But still, we want to investigate different features here and identify them, maybe count them. But in the first view, when you start, the first experiment is usually, anyway, just seeing what you can see and how you can see it to get an idea how you can continue with the analysis. In some cases, you have long history with that kind of images, then of course you know, okay, I need to get to these different parts here, and actually I'm not a biologist, so I can't tell actually what the cell components are, but anyway, you need to then you know that you want to identify specific shapes in this image, and then you can do the analysis more directly, and then you can start also making a hypothesis on how the cell is growing. So what we want to do, often it ends up in some kind of imaging experiment. This is an example where we do tomography, where we scan the sample. In this case, it's a bone sample. We get projections looking something like this. So this is just a transmission. The X-rays are going through the sample, and you measure the shadow. And from the tomography process, you can get a three-dimensional reconstruction where you really can see the bone, some porosities. I believe that is probably some marrow. And then you can do analysis on the shapes in here. Those shapes are not so easy to see actually in that one. You can see maybe there are these pores, like stripes in this projection, but it's more guessing than really telling. And doing a scan of this type produces a lot of data. As you can see, we end up in 56 gigabytes, and then you do the filtering that we talked about last week, producing even more data because you still want to have your original, maybe, and then you want to have the filtered one, and then you even get more data. But at least it's less noisy, so we need to do some kind of reduction now. And that kind of reduction is a way, a step in the way to get to these single numbers that we want to measure actually. So here we can look for maybe volume fractions, cell counts, cell stretch, so that's a shape measurement, also volume variability, and all these measurements, you need a step to get there. And that is the question how we can do it. And that is where the segmentation comes in. Segmentation is when you tell that this region belongs to that kind of material, that region belongs to another type of material, and that region belongs to the void around it. And there are very many ways of doing segmentation, and sometimes it's there are very easy ones. Other cases, you really need to go into advanced methods, complicated algorithms that do this segmentation. You may go into machine learning, where you train machine learning model to identify these objects. But all these more advanced approaches usually also mean that it takes time. So if you can use something simple and get the results you want, don't do the heavy stuff, because you save time in doing the simple one. And if it doesn't bring very much more to your measurement, there is no point. So you have to select and be aware of that there are very many methods, and also what some of them have as advantages and disadvantages. And actually, this and the next lecture will be about segmentation, because it is a very central topic in the quantitative analysis. So, a little bit review from last week. We had this ugly image that we want to get nicer. And I didn't really say why we want to get it nicer. But anyway, we have our image, which is degraded by blurring, noise of different kinds, artifacts, and then you get this ugly thing. And typically, what you get after applying a filter is you have the real filter of the real information plus filtering of the noise. And the ideal case is that we have much more of the information that we want and much less of the noise and the things we don't want. If you have a bad filter, of course, then you more or less suppress the relevant information and enhance the irrelevant information, but that is probably something you always already reject when you see it. So the question is what we now get from an imaging modality. And if we look at this image, it's an X-ray radiograph of a rubber duck with some, I think it has some flashing effect in it, so there is some electronics. So what we can see is, first of all, we have a thin wall, so it's not a solid object. We can see that there is some electronics, and in particular, there are two batteries. There are some solder points, and I believe that is the LED that does the nice flashing of the duck. So this is what we can see from the radiograph. It tells a little bit about where it is, but you don't know where it is in the depth. We can look here at the gray level histogram. We see that there is a high peak, which corresponds to the background, and then there is some peaky part here. That's probably the void in the duck, and then it goes down all the way down here, and that is probably the part that belongs to the battery. So you can see from the histogram already that we can identify regions based on their gray levels. And here, if we would simply say we want to know where the batteries are, we would focus on these gray levels here. And I believe if we just say everything greater than 0.3 or something is turning white and below turning black, then you would probably see the batteries, possibly some of the solder points as well. So that would be a first way of getting information from a segmented information from this image. There are different approaches of doing this, and I had this figure before. I modified it a bit because in the previous version it said machine learning here, and I think machine learning is a specification of data science. So data science is a whole workflow that includes the machine learning, but it's also the way how you work with the data. And so I changed that one. Then we have the experimentalist who knows how the images are formed and try to extract information through that formation process. And you have the computer vision approach, which means you have a toolbox of all nice algorithms, and then you apply them and see what you can get. And let's approach these in different ways. We have the model-based approach, which the experimentalist is more going for, top-down, and often has a reality-based model. If you go to the data scientific approach, which includes computer vision, deep learning, then you're more result-driven. So you need to know what you're aiming for before you can do it. So you need actually sometimes to have the training data to see what the result actually should be. And then you can apply it to unknown data afterwards. The model-based approach, we have seen this one too, I think in the first lecture. So you have some kind of excitation that you let go through a sample, there is a response, and that response is collected by a detector. This is, in principle, what is happening in all our imaging systems. If it's just a camera looking at natural views, or if it's a radiation X-ray, neutron-based, or if it's ultrasound, whatever. You have the same principle. And how the images look like depends on what you have done, what kind of modality you use. Looking at that in a real case, we have the rubber duck again, and we see what it should look like, and then we let the propagation go through. You also need the beam profile as a reference. You also need to detect the bias, and then you get your measured image. And when you normalize the images, which is a typical step, you should get back to some sample profile looking like this. And we can look at different profiles here. What can happen if you don't normalize correctly is that you can have inhomogeneous illumination. And looking at this plot, I just took a profile about at this height. And then you can see here, this corresponds to the wall, this one too. This would be the area of the battery. And you can see that there is a deviation here. And the true image should have a transmission 1 out in the void, and then it's getting less if you go inside a sample. But there are different effects here. First, you have the beam profile that behaves a little bit differently, and you see this little tilt here. That's actually a scattering effect from the sample. It's also a physical effect that you may have to correct for later. So it gives you some kind of glowing halo around the object. So when you normalize, you get the, say, correct profile. It's flat outside, ideally. And that is what we're going to work with later. But all these inhomogeneities in the illumination can make it very hard to analyze. For example, in tomography, you have an effect called beam hardening that also makes the edges much brighter than the middle, and that gives you like a cup-shaped profile through the sample, even though it should be flat. So then we have the whole absorption imaging, which applies to quite many different types of imaging. It's based on our Bayer-Lambert's law, where you have some source and you have the sample effect. And that is the negative exponential with an attenuation coefficient and the propagation distance. And if we now want to segment things, we could say, again, looking at the gray levels, we can see some information, but it's not always easy because we have the shape of the object too. It's not a flat object. Usually it has some undetermined shape. Well, you know the shape when you put it in, but anyway, it's not known to the equation in such sense. And it's not directly derivable. Let's look at an example. We have transmission imaging in 1D. We have 3 materials, and we have material 1, 2, and 3 with different attenuation coefficients, and we even have a little uncertainty in these attenuation coefficients, so there is a natural variation. It's not necessarily that it's exactly the same everywhere. So if you look at natural objects, can be the body, piece of wood or something, then you have density variations within the material due to how wet or dry it is, and so on. And that can give you this natural fluctuation. So what I do here in this example, I create some random distribution of what the beam penetrates through the material, and then I get the detector readings for these materials at different thicknesses. So looking at what we have our attenuation coefficients, and we have what the detectors see here. And you can see that there is, first of all, you have this exponential decay, and you have some spread. And if you look at what you measure, you see you measure a lot of variation within material 1, and then it's getting more and more narrow. And the interesting thing is that material 3 is quite narrow here, but in our model, we had it actually set to be quite wide. And that is thanks to this exponential law. And it also makes it harder to interpret. So you need to actually compute the logarithm of the normalized image in order to get a realistic variation within the data. So here is again the normalization, where I have the measured image. I take off the bias, which is the camera effect. We have the source profile, and also that one has the detector bias, and then afterwards we get this normalized image without any stripes or inhomogeneities in the background. And after normalization, we expect 1 in the void, and between 0 and 1 when it's in the sample. And if the sample is opaque, for example, if you would put a piece of lead there, the beam wouldn't go through, and then you would have a 0. Ideally, because again, you have noise, and the noise could make it that you actually get negative values. But from the physical point of view, you cannot be less than 0. So let's take an example of a real image. So let's start from the real image, and then we go through the modeling. So here we have a radiograph from a mammography, and you can see here is the shape of the breast. There is some lump that we want to identify. And again, it is about using Beer-Lambert's law. And to test this, we make a little, or to explore what we can see here, we make a model where we have first air is 0 and breast tissue is 0.01. And in this case, we have to work through this model. So then we have to do a line integral through, and in the practical case here, we actually work with a sum because we have voxels in our model. And looking at this, we can create our model. We say that the breast is modeled by a half a sphere. And I think that one I need to execute. Yes. And then we set that within the breast we have the alpha is 0.01, and the pixel size is 0.1 centimeters. And then we have the volume is the product of those. And then the detector signal here is the exponential of minus pixel size times the sum along the volume. And then we get a profile like this. So this would be our simulated radiograph. And you can see that the intensity profile goes from 0.9 about up to 1. And 1 means that we have just free air propagation. And looking at the histogram of the gray levels, we have the background pixels. It's a huge peak. And here it appears that we have a linear distribution decay within the breast pixels. And the reason why we have that is we have first in this part, which is the longest distance, we also have the most gray levels, and then it is decreasing the further out we get. And then we can also, from this, we can actually use Beer-Lambert law to compute the thickness. And that is something we do a lot in neutron imaging. We always want to compute the water content in an object, and that can be done through that. And in principle, what we need to do is to compute the I detector, the negative logarithm of I detector, and divide it by the attenuation coefficient. That requires that we know the attenuation coefficient. In medical applications, I would say it's pretty well known, also with uncertainties. In other applications, you don't really know it, so you have to measure it. And if you're interested in how to do it, I can give you some links to some tutorials that I made on how to quantify the attenuation coefficient. So this equation turns into this little code here. So it's actually just straight off. And from here, we can now get the thickness, the local thickness in the object. So here we can see that in the middle here, we have the thickness 10, and then it tapers off and goes down to 0 when we go out in the void. And of course, the thickness histogram is flipped, because here you have the void is no thickness at all, and then at that point here, you have the highest thickness. This would be our model, what it looks like. So that would be a visualization of the thickness. And let's see. I thought that one would be. No, that wasn't a good idea. Okay, I should have stepped through the object. So it works if you have done all the steps in advance. Then you can actually rotate interactively with a model, something you can maybe use for your own visualizations also. So typically, as we saw in the first image here, we have something that we want to look for, and in that case, our attenuation coefficient is not constant, so then we need to do some kind of analysis and to be able to tell. And from first view, you can't tell if it's because it's thicker or because there is a change in material composition. You can't tell that from the radiograph. You can tell it from your experience that this is not natural to be there, but you can't measure actually that it's there. So let's add or expand our model. So now we have this lump inside, has twice the attenuation coefficient, and we place it as a little sphere inside. And in these slices through the model, it's quite obvious that's there. But if we start looking at the detector image, it's not really obvious. I mean, that gray level is also found about here. That gray level is also found here. So it could be both sound and it could be the lump. You don't know. And that is a problem when you look at radiographs to interpret them in the correct way. And what you also see if you look at the histogram, we have an increase of these very thick gray levels, and you have a decrease in this area, so you have a redistribution of the histogram. You could maybe claim that, okay, this can be used for detecting objects, so just comparing the histograms, but it's a quite blunt tool because there are so many factors involved that just comparing the histograms is very difficult. And the other thing is, it's not always that you have the healthy case radiograph. It's more like the exception. In particular for mammography, there is this regular screening, and in that case you could actually tell from that, but still the histogram is not the tool that you should use to compare. But here we just look at it for the model's sake. And of course we can turn it around and we can see that the thickness map looks also a bit redistributed, which is natural if you looked at the the intensity map. And if we would look at the thickness profile, this is what the breast should look like if it was the same material. So that is not really natural. So from there on, we could conclude that it's not the real thing. But if you have this undefined shape that you work with, it's not easy to determine just from the radiograph what you have. And one reason is that if you look at this example, is if you have two materials, I have attenuation coefficient of alpha 1 is the same as 2 times alpha 2. That means if you read here the same intensity, it could have been that we have a short distance of alpha 1 or we have a long distance of alpha 2, and we can't tell which one is what. So this is the kind of ambiguity you have to work with if you work with the radiographs. There are different ways of solving this. One is to still use transmission imaging, but confine the object within a known shape, constant thickness, and that's actually also done in mammography, and also what we have done in our plant experiments. Instead of having a round pot, which is, say, the traditional way of growing plants, we instead started using slabs, because then the roots, and the soil has a constant thickness, and the roots, they are the deviation, and then we know, okay, there is actually the root, and we know it's a root. The other way to get around this ambiguity is actually to use a modality that provides three-dimensional information. So that would be using computed tomography. And of course, this is used a lot, but in some cases, it's not feasible, maybe not even ethically motivated, because if you start doing tomography, you also expose your patients to a lot of dose compared to if you do a radiograph. And also, it's a time factor. If you want to do many samples, high throughput, then also tomography takes longer time. It's harder to analyze due to the data amount. So the radiograph is still a method that is used a lot. So that brings me to the end of the image formation process. It's a bit early, but anyway. So first, the conclusion is that the images we get from the detector, they are somehow distorted because of the way the acquisition formation process is happening. Also, it could be that there is noise. So you need to do the normalization first before you start doing any analysis. And also that transmission images, they are often very difficult to interpret. We have plenty methods to do it still, but there is an ambiguity. And let's see, I could, in principle, let's see if I can find that one. Yes. Where is my mouse? There it is. So let's go here. Oh, there is a lecture. This is also online. This is part of a tutorial that I made once, and here it's about measuring the attenuation coefficient. So if you don't know the attenuation coefficient, there are different ways of doing it, and what we typically do is we have something called a step wedge. So we have an item with increasing thickness, and that item can then be used in order to extract what our attenuation coefficient is. And then we get our images like this, and you can see here how the transmission information comes through to the detector, and that is what we get here. And that can then, in a couple of steps, let's see, there's a lot. Oh, this was not the solution. Okay. Anyway, you get measurement points for different thicknesses, different intensities, and through that you can do a linear fit. And that fit gives you the attenuation coefficient. And one more interesting thing, let's see if I can find that one. Oh, no. Yeah, here. This is actually a model that, see, can I do that as a, no. Let's see. That was not supposed to be, okay. This one is not prepared to be a lecture. It's more do-it-yourself tutorial, so nope. Hello. So, yes. The interesting thing is that you can actually also determine the thickness of one element by doing a reference measurement. And what we do typically is we have a reference image of the sample without water, and then we do some processing, filling in water, taking out water, whatever, and then we do an image of that, and by subtracting the images you can in the end actually quantify how much water you have. And typically we can, with that technique, we can be within 5% uncertainty in quantifying the water content in our images. So this is something we do a lot, particularly with people in geology and soil sciences, environmental sciences. And it has even gone to the point that we even can quantify the root water uptake through this technique. Yes, so these notebooks, I can give you the links to them, and then you can take a look at them yourself if you want. It was just a side note because I had some minutes left now. Yeah, and there is actually also the whole solution is on the same webpage. And if you want to listen even more to me, then I am explaining in some YouTube videos. So I think that is